Are we supposed to be doing number one?
You can start right now. I was just about to do a quick intro. It's 4:10, so we'll get started today. Maybe a few more people are still rolling in. So happy Thursday. So today we're going to keep working on chapter 3 and do some more stoichiometry stuff. So on today's worksheet, I have a few problems with unmuted, right? Okay. I have a few problems with Avogadro's number and stuff like that. And then another problem finding the empirical molecular formula. And then we're going to get into today some problems with chemical reactions. So that's what we'll do today. And then wherever we finish or wherever we stop today, we'll pick up on Monday. Once again, if you guys could go into the chat and put your Iowa State email, that would be great. I can mark down attendance and my boss knows that I actually do my job. Are there any questions from you guys before we start today?
Are we ever gonna go over like the limiting reagent and like percent yield?
Yes, we are.
I second that.
Okay, so that I have percent yield today, and we're going to start on chemical reactions. And I plan to talk about the limiting reagents on Monday. Am I correct? You guys don't have an exam tomorrow, right? It's next Friday. Okay.
Correct.
Yep. So what I want to do is make sure we get a good basis of what a chemical reaction is and how to do calculations with it. And then we'll start digging into the limiting reactants. Good question, Sarah and Ben. Any other questions? All right, so why don't you guys, I'll let you guys start working on these, but first I want to review what we've been talking about the past couple of days, which is moles. Now, there's 3 different states which I boxed here in pink. So you can have grams, you can have moles, or you can have atoms and molecules. Now, to go between these, we're going to use 2 things. If you're going from grams to moles, you use molar mass, which is grams per mole, and you get this from the periodic table. And if you're going from moles to atoms and molecules, you use Avogadro's number, which is 6.02 times 10 to the 23rd. So you always have to go along this line. There's no way to go from grams directly to atoms. You have to go to moles first. So if you don't have this, I recommend you take a picture or write it down. And if you didn't grab it, just feel free to message me in the chat and I can scroll back over for it. So why don't you?
Since we only have one atom in number one, wouldn't you just multiply it by 6.022? 10 to the 23rd.
Okay, so yeah, so Ben asked for number one. Number one says, how many total number of atoms are there in 1 mole of iron dichromate? So yes, Ben, you would multiply by Avogadro's number, but that wouldn't give you atoms. What would that give you?
I thought that would give you atoms from moles.
So that will give you molecules of iron dichromate. So then what you have to say is you have 6.02 times 10 to the 23rd molecules. How many atoms are there in each molecule? So there's 2 iron atoms, there's 6 chromium atoms, and there's 21 oxygens. So what you'll have to do is add up how many atoms are in one of these, the number of atoms.
29.
Yeah, I think it's 29. And then you multiply that one by Avogadro's number. So try to work on numbers 1, 2, and if you're ambitious, you can try to work on number 3, and then let me know what questions you have, and we'll come back together in a few minutes. I just muted everyone. Just had a message about the background noise. Just make sure when you talk, just unmute, and then when you're finished talking, if you can mute again. Okay, so we can start working on these ones together. And if you're stuck or you didn't finish, that's completely fine. So number one, how many total atoms are in 1 mole of FeCrO CR2O7? So this is iron dichromate. CR2O7 is one of the polyatomic ions. Now, let's add up the total number of atoms in 1 molecule. So the 2 here means we have 2 irons. So 2 irons. For the chromium, we have, well, there's 2 chromiums here. But this 3 on the outside, this means that there are 3 of everything in here. So we have to do 2 times 3, and that gives us 6. And then for oxygen, we have, looks like 7 inside the parentheses. And then this 3, once again, this applies to the oxygen too. So 7 times 3 is 21. So the total number of atoms in 1 molecule would be 2 plus 6 plus 21, which is 29. So that's 29 atoms in 1 molecule, but the question asks how many atoms are there in 1 mole? So we need to use Avogadro's number here. So first thing you write down is write down what you have. So we have 1 mole, and then draw out a bar. Make that a little more clear. So this is 1 mole of iron dichromate. Now, how many molecules are in 1 mole? Well, this is where we use Avogadro's number. So going from moles to molecules is 6.02 times 10 to the 23rd. So we put moles on bottom so that the units cancel, 1 on top and 1 on bottom. And we put 6.02 times 10 to the 23rd molecules on top. Molecules, sorry, my handwriting. So look, we have 1 mole on top, and the unit cancels 1 on top and 1 on bottom. That's how we know we have to put the mole on bottom and the molecules on top. You always put 1 on top and the other one goes on bottom. Okay, so now we have molecules of iron dichromate, but the problem asks for atoms. So again, let's put molecules on bottom so that it cancels on top. So 1 molecule has how many atoms? Well, we just found how many atoms are in each molecule. It'd be 29. 29 atoms. So now our units of molecules will cancel, 1 on top, 1 on bottom. And our final unit is atoms. So when your final unit is what you're desiring to find, that's when you know you're done. So now what you got to do is take 1 times 6.02 times 10 to the 23rd times 29. And that will give you, let's see, with 3 sig figs, 1.75 times 10 to the 25th. Can I get some head nods if that's what other people got? Okay, nice. That's a 25 there. Yeah, again, I'm sorry, I'm kind of slow at writing. I'm using my mouse. So that's total atoms in 1 mole. Okay, so let's move on to number 2. Number 2 says a solution of ammonia and water contains 34.8 moles of water and 8.10 times 10 to the 24th ammonia molecules. So for this, you have to use back your chapter 2 knowledge. What is the chemical formula for water? Well, that's pretty easy, H2O. And what is the chemical formula for ammonia? This one might be a little more evasive. This one is NH3. So those ones would be ones that you are expected to know. So we're going to do the same thing that we did up here. So let's write down what we start with, 34.8 moles of H2O. And write that in the top left corner and draw out your unit conversion bar. Now, we don't want moles of water, we want hydrogen atoms. So again, to get rid of the unit of mole water, we put that on the bottom. So 1 mole H2O goes on bottom. And we want to go to molecules of H2O. Oops. We want to go to molecules of H2O. Well, how many molecules of water are there in 1 mole? So again, this is always going to be the same number, 6.02 times 10 to the 23rd. Molecules of water in 1 mole of water. Now again, our unit cancels. We have mole water on top, mole water on bottom, so that goes away. And so now we have molecules of water, but we don't want molecules of water, we want hydrogen atoms. So take this, take the unit that's on top and write that on bottom. So 1 molecule of H2O. And on the top, we want to put hydrogen atoms. I wrote H atoms there for hydrogen. How many hydrogen atoms are in 1 molecule of H2O? Well, you just look at the formula. It says H2O. So there's 2 hydrogens in 1 water. So again, if you're doing it right, your units, molecules, water cancels. And now you can do your calculation. So again, multiply across the top and divide the numbers across the bottom. And if you do that, you should get 4.19 times 10 to the 25th hydrogen atoms. So 5. 4.19 times 10 to the 25th hydrogens.
Wait, wouldn't there be? Oh wait.
Did I make a mistake somewhere?
Well, I was thinking like, isn't the amount of hydrogen atoms in H2O 2/3 of the actual count? Because there's 3 like atoms total, but there's only 2 of them are hydrogen.
Right. So you could do what we did up here. You could do 1 molecule is 3 atoms, and then multiply that by 2/3. You're going to get the same answer. In this case, we just said, we skipped the total part and we just said, well, H2O is 2 hydrogens, so we're going to put 2 on top. Does that make sense, Dylan?
Yeah, kind of.
Okay. Yeah, I know this is kind of weird stuff. The only way really to learn it, in my opinion, is just to do practice problems, and it'll come to you slowly. Okay, and then, but we also had some ammonia in here. So we had 8.10 times 10 to the 24th NH3s molecules. So 8.10 times 10 to the 24th NH3 molecules. And we want to figure out how many hydrogens are in this. So put molecules of NH3 on the bottom so that it cancels with 1 on top. And then how many hydrogen atoms are in 1 molecule of NH3? Well, it's just 3. We're just looking here. It says H3. That means 3 hydrogen atoms in each molecule. So our units of NH3 molecules cancels. And to get this answer, you do 8.10 times 10 to the 24th times 3, and that will give you 2.43 times 10 to the 25 hydrogens. So now you have the amount of hydrogen in the water and the ammonia, and then you just have to add these for a total. So your total, when you add these, you should get, let's see here. I got a total of, let me do it in red, 6.63 times 10 to the 25th hydrogen atoms. Now, sometimes these problems, the hardest part is doing the calculator portion. So just what I recommend is get a calculator out that you feel comfortable with and that you're going to use for your exams, and then just try to punch these out. And if you can't get the right answer, if you have the same work but you can't get the answer, please let me know and I can help you out one-on-one. What questions do you guys have on number 1 and 2? Okay, so I'll try to leave this work up when we look at number 3 here, or number 3. So we did one like number 3 yesterday. So why don't I give you a couple minutes to try to see if you can work this out on your own, and then we'll come back together in a few minutes.
Is CX an element?
Yeah, sorry, that was a little confusing. The X's are supposed to be numbers. So like it's carbon something, hydrogen something.
Okay.
Does that make sense?
Yeah, a little bit, I guess. But
So it would be like C5H20 or something, or C4H8. So what you're trying to do is trying to figure out what are these numbers in this.
okay.
It's just like the one we did yesterday, Ben, if you remember.
Yeah. I got 4.7 as one of my, that doesn't seem right. You said we'd never get that, would we?
No, I did not get 4.7 either.
Did you?
Maybe when I'm doing it, maybe you'll see where you made a mistake, or maybe I made a mistake. We'll see. It shouldn't come out to 4.7 though. Okay, so feel free to keep working as we start doing this one together. So this is a classic problem for Chem 177. It's finding the empirical and molecular formulas. So let's decipher the information here. So it says there's 82 82.63% carbon by mass. So carbon 82.63%. So if carbon is 82, what percent does the hydrogen have to be? How would we figure that out?
You put it out of 100, like out of
Yeah.
100.
Yep, right on, Dylan. So the total has to be 100%. So this would be the remainder, so 17.37%. Just do 100 minus 82. So now how do we find the chemical formula here? My camera is spazzing out. Can you guys hear me okay?
Yep.
Okay. So here's how we do this. You take the carbon, and we want to assume that we have 100 grams. So that would be 82.63 grams. And then hydrogen, again, we're going to do the same thing. Assume that this is 17.37 grams. And we're going to divide these by their individual molar masses. So where do we find the molar masses? So on the periodic table, it's the number under the element. So carbon is 12.01 and hydrogen is 1.01. So we're going to divide these by their molar masses, 12.01 and 1.01.
I did by that big molar mass. Why wouldn't you do that?
So does anyone know why you wouldn't divide by this one here?
Because that's like what you're supposed to get, like out of the, like it's what the molar mass is supposed to be.
Okay.
I guess technically.
Right. Yep. So we're going to use that for finding the molecular formula. And what we're doing right now is we're saying, if we had 83 grams of carbon, what would be the equivalent amount of moles that is? And in that case, you have to divide by the molar mass of just carbon. So we do 82 divided by 12, and you get 6.880. And you do for hydrogen 17 divided by 1, and you get 17.198 about. Now, once you get these ones, the next step is to divide them by the lowest of these. So whichever one of these is the lowest amount, that's what you want to divide by. So the lowest of this between 6 and 17 is 6. So divide by 6.880 and divide this one by the same thing, 6.880. And that should come out, when you divide this, you'll get just a nice even 1.0. And when you divide this, you should get about 2.5. Now, who can tell me what these numbers mean? Does anyone remember from the other day, what do these numbers mean?
2.5, you would double the number because it's 0.5.
Right, yep, exactly. So these are the numbers of your chemical formula. So this would be C1H2.5. Now, again, we can never have a half of an atom. That doesn't exist. So we're going to double everything here. So we're just going to double everything. So this becomes C2H5. And this here would be your empirical formula. So that is the empirical formula. And just to refresh your memory, the empirical is like the simple version of the formula. So part one is good. Now the question is, what is the molecular formula? And the way we do this is we say, what is the molar mass of C2H5? Well, if you go to the periodic table and you add up 2 carbons and 5 hydrogens, we get that this molar mass is 29.07 grams per mole. So grams per mole, all right. But the problem says it should be about 58. So what is the relationship between 58 and 29?
How did you get 29.07?
So does anyone know where I got this 29.07?
You added what the weight would be of 2 carbons and 5 hydrogens.
Right, yep. Okay. So the periodic table, hydrogen is 1 and carbon is 12. So if you add 2 times 12 plus 1 times 5, you get the molar mass for this one, which is 29. Well, look, 29 is 2 times, or is half as small as 58. So if you want to confirm this, do 58 divided by 29, and you see that it's equal to 2. So what this means is our chemical formula should be twice as big. It's telling us in the problem it should be 28 or 58, which is twice as big as what we have. So that means you have to take your formula here and multiply everything in the formula by 2. So it would be C4H10. So again, we're comparing the molar mass, what we have. It should be double. That means we have to double everything in the empirical formula. And this gives the final molecular formula, or the actual chemical formula. What questions do you have on this problem?
None.
Okay. I know these problems are confusing. They take a while to learn. So if you have a question and you want to ask it personally, there's a way to type it, a private message in the chat. Or I can maybe answer your questions afterwards. So I want to move on to number 4, which is in regards to a chemical reaction. So let's read this problem, and I'll give you a minute to copy it down to your paper. And then we can discuss how we would go about this. So number 4 says, the decomposition of sodium azide, which is NaN3, into solid sodium and nitrogen gas is used to inflate airbags. And the question is, what is the balanced chemical equation for this reaction? And then it asks, if you were given 1.3 moles of the sodium azide, how much N2 gas would you form? That's part B. And then there's a similar one for part C. So while you're getting a chance to process this and write it down, let's talk for a minute about chemical reactions. So in a reaction, we always have an arrow, and we have something on the left making something on the right. Does anyone know what the objects or the chemicals on the left and right are called?
The ones in the front are the reactants, and the one on the other side of the arrow is the products.
Okay, yep, good job, Dylan. So these are the reactants. And then on the right, these are products. So pretty straightforward. You're reacting some things, and then you draw an arrow, and then products is what it's going to make. So you might remember doing this if you took like a high school chemistry class. So let's do part A. Write a balanced chemical equation for this reaction. So what is being reacted in this one? So it says you are decomposing sodium azide, NaN3, and it didn't say it was solid there, but I should have put that. And then you put what the state of matter is in a parentheses. So that parentheses S, that means it's in a solid form. And it tells us it's producing solid sodium, which is Na, and parentheses S for solid. And a plus sign, it's also producing nitrogen gas. So nitrogen gas, like that. And the G means gas. Does anyone know, there's something I'm missing in this formula. Does anyone know what it is?
Wouldn't it be N2?
Okay, yes, right, Ben. It would be N2. Why would it be N2?
That's just how I always see it, I guess.
Okay. Yep.
I think,
so
isn't it like one of those, like oxygen's one of them too, and like fluorine, it's like the ones that like are on their own, you have to have two of them.
Yep, exactly, Dylan. So I'm trying to see what worksheet we discussed this. I have them listed here. Let's see, maybe it's on worksheet 2. But yes, so there are some atoms that are just, here they are. So take a picture or write this down right here. There are certain elements, like Dylan was saying, that are just come in pairs. We call this the naturally diatomic elements. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So write this down like on the front page of your chemistry notebook. You're going to use this all semester. So there's 7 of these, and I'll type it in the chat if you didn't get it copied down quite in time. So you are expected to know these. You are expected to know that when it says nitrogen gas is produced, that is N2, not just nitrogen. And this is going to come up all semester, and is just one of those things you have to know, or you're going to be guaranteed to get the problem wrong. So N2 here. So we have our products and reactants. And the next thing we have to keep in mind when we're doing chemical reactions is that it's balanced. Now, does anyone want to explain what do I mean by balanced?
The same amount of atoms are on each side of the reaction.
Okay, and Dylan, why does that matter?
Because of the conservation of mass, you have to have the same amount on, like, it can't be like destroyed or created, so you have to have the same amount on both sides.
Yeah, great. So Dylan was saying, look, if you've got 3 nitrogens here, you got to have 3 nitrogens on the right. So this is called balancing an equation. So the way I do this is under the arrow, I like to write the elements we have. So we have nitrogen and sodium, and just write down how many we have on the left. So we have 1 nitrogen or 1 sodium and 3 nitrogens. And on the right, we have 1 sodium and 2 nitrogens. So these need to be equal to be a balanced equation. So on the right-hand side, we need more nitrogens. So the way you do that is you adjust the coefficient. So I put a 2 in front of this nitrogen. That means that there are now 4 nitrogens on the right. So I'm going to scribble this out, and there are now 4 nitrogens. Well, I just created a problem because now I have 4 on the right and 3 on the left. So I'm going to have to put a 2 in front of here. And so this is going to bump up the sodiums to 2, and it's going to bump up the nitrogens to 6. We have 2 and 6. And then on the right side, well, we need more sodium, so I'm going to put a 2 in front of the sodium. We have 2 here. And I'm also going to increase the number of nitrogens. So if I put a 3 here, we get 6 nitrogens. So now we have the same number of atoms on both sides. So I'm gonna maybe I'll keep that and just move this piece down. So this was part A. So now we have a balanced reaction. We can work on part B and C. So why don't I give you a minute or so to try to think through how you would go about part B and C.
Have we done?
What's that?
Have we done the ones like B?
We have not. Nope. So just think about it. Just try to think about it conceptually, and then we'll do it actually using math. If you, yeah, I'll shut up for a minute, and I promise we'll come back, work on them together. Okay, so maybe you've got just a second to think a little conceptually about this. So part B says, how many moles of N2 gas are produced from 1.3 moles of NaN3? So let's write down what we have. We have 1.3 moles of NaN3. And we're going to be doing a stoichiometry conversion, so I like to just draw out a line like that. Okay, so we want to get from moles of NaN3 to N2. So I'm going to put moles of NaN3 on the bottom so that it cancels with the one on top. So I'm putting moles NaN3 on bottom, and I put what my desired outcome is on top. So I'm desiring to go to moles of N2, so that goes on top. Now the question is, what is the ratio between moles of N2 and moles of NaN3? Does anyone know where we would get these numbers?
From the equation.
Yeah, so Dylan said we get these from the equation. So that's why we balanced it. What we balanced here is we said 2 moles of NaN3, so I'll put 2 here, and makes 3 moles of N2. So we have a 3 to 2 ratio. I'm literally just taking the numbers from the balanced equation. And once again, always make sure your units are canceling mole NaN3 on top and bottom. So what you do now is you take 1.3 times 3 divided by 2, and you get 1.95 moles of N2. And I guess technically, since it's 2 sig figs, I should write 2.0. All right, 2.0 moles of N2 gas. Okay, now moving on to part C. Part C says, how many grams of NaN3 is needed to make 23 grams of N2? So this is going to be very similar, just we're going to do it in the reverse process. Move this one down a little bit. There we go. So write down what you have. You have 23 grams of N2. Now, can we go from grams directly to other grams? I see some heads shaking no. What could we use to go from grams to moles? So we have grams. So this is where we use the molar mass. So let's put grams of N2 on bottom because we want to get rid of N2, grams of N2, and we can go from grams to moles of N2. Now, what is the conversion here? So this is when you're going to need to look at your periodic table and see what the molar mass of nitrogen is. So scroll over here, nitrogen is in the top right corner, and this number here is 14.01. So 14.01, but we have 2 of them. So that means it would actually be 28.02 per 1 mole. So the number on the periodic table is 14, but because it's N2, you double it. So now we're going to use, let's cross out our units. So grams of N2 cancels on top and bottom. All right, so now we have moles of N2 on top. So we want to get rid of moles of N2, so we're going to put that on the bottom. And what our desired thing is, so we're desiring to go to moles of NaN3. So we have a mole to mole ratio. So again, here we're going to look at the periodic table, or excuse me, the balanced equation. So we have 3 N2s makes or requires 2 moles of NaN3. So I'm grabbing the numbers right from the balanced equation. And then once again, moles N2 cancels top and bottom. And now we are going to use the molar mass of NaN3. So again, put moles of NaN3 on bottom so that it cancels with the moles of NaN3 on top. And put grams of NaN3 on the top because that is what you desire to go to. So 1 mole is how many grams? Well, let's look on the periodic table. So, oops, polyatomic ions. Okay, sodium is on the left. This has 28 or 22.99. So we go 22.99 for sodium, plus for nitrogen it was 14.01. But remember there was 3 of them. It's NaN3. So 22.99 plus 14 times 3. And where did my answer key go? I'll just type it in real quick. So 22.99 plus 14 times 3. We get a molar mass of 65.02 grams per mole. So 65.02, we're going to put this into our equation here. 65.02 grams of NaN3 per 1 mole. And once again, look, our units, mole NaN3, canceling top and bottom. So to do these calculations, again, I recommend you try this on your calculator. Multiply everything on the top and divide everything on the bottom. So 23 times 1 times 2 times 65, divided by 28, divide by 3, divide by 1. And I lost my answer key, so I'm going to do it myself. And I recommend you try it as well. I got that this would be 35 point, what are we doing? I think we're doing 2 sig figs. So this would be 36 grams of NaN3. What questions do you have on this problem? Okay, so I think, so we only have 4 minutes left in the session. I think what we'll do is we'll stop here for today. And on Monday, we'll talk about limiting reactants and more complex stoichiometry with limiting reactants. So if you want to have a problem to do before next session, you can check out or take a picture of number 5 here. Otherwise, we'll do this one on Monday. Otherwise, have a good weekend. If you guys have any questions, feel free to stick around for another few minutes. Otherwise, we'll see you guys on Monday.